Hi everybody, welcome to another video on Calculus 2. We go to section 8.9, Improper Integral. So in this section, when we talk about improper integral, it is going to be definite integral, meaning the integral that has the limits. So, like this. And what makes it improper will be due to two things. The first one is infinite interval. So when we talk about a definite integral here, what makes it improper? One is the limits. There's a problem with the limit, and then two, there will be a limit with the function. So the first one we have is due to the infinite interval. So that is the problem with A and B. And then the second one we have is due to the unbound integrand. So the problem with the function. Unbounded integrand. So the problem with the limit, then the problem with the function. So the first part of the section is the problem with the limits. Infinite interval. So we will have three cases. The first one is where we have the function that continues from a from a number constant to infinity, and then the second one is from negative infinity to a constant, and the third case where both of the limit are negative infinity and infinity. So three scenarios. When that happens, what we do is we'll replace the upper limit with b, and then we'll just find the limit like we normally do, and then take whatever the result is, take the limit for b go to infinity. For the upper limit, we usually use b. For the lower limit, we use a. And when we have both of them, negative infinity and infinity, we have to split into a c, any number in between infinity and negative infinity and infinity. Pretty much any number will do. And then we will have both the lower limit and the upper limit for that. So if it is infinity, replace with the number and then take the limit, and then we just integrate. Right. Now, what we call if the integral is divergent, if the limit does not exist. If the limit exists, it is called convergent. Right. So I just problem with the limit, replace with the numbers, do the integral, and then evaluate the limit. So it's not nothing that we haven't learned before, just a terminology here. Right. Before we go to that, let's look at the two common functions. First of all, this function is y equal to e to the x, and we focus on two things. What happened as x goes to infinity and x goes to negative infinity. Right. So when x goes to positive infinity, e to the x goes to infinity, and when x goes to negative infinity, e to the x goes to 0. Yeah. So that exponential function, and this is the logarithmic function. That should be ln of x, or actually any base will behave the same. And we have as x goes to infinity, ln of infinity goes to 0, so ln of x goes to 0, I mean infinity. Yeah. So y values just get bigger and bigger, essentially goes to 0, goes to infinity, sorry. And now we have this, that is, as x goes to 0 from the right hand side, ln of x goes to negative infinity. And note that ln of x is undefined. For x less than or equal to 0, so it is undefined on this side, and we have the limit on the other side. Also, something that we know, e to 0 power is 1, and ln of 1 is equal to 0. We might need to use that later. Right, so pretty much that. This is just a little review. Now, just go to the first example, see what do we have. Right, so evaluate the improper integral, that one. So first, every time we see infinity, the first thing we do is replace that with the limit, make it proper integral. I think that's better. Right, so first, infinity, so I will change the upper limit, so we use b. And the limit replaced to b, where b go to infinity. So that's the first thing we do when we see infinity. Right, now we just integrate this, and this should be easy, right? We have the limit, don't forget there's the limit. Now integrate e to negative 3x, integral is e to the negative 3x, but it is integral, so we will have divided by the coefficient of x, and go from 0 to b. Now we're going to substitute b in here first. The limit is the last step of the problem. Now substitute b in here. So first I have negative 1 over 3 e to the negative 3b. So that's where we substitute in b. And then we subtract where we substitute in 0. Now, e to the negative 3 times 0, we have e to the 0 equal to 1. So because of that, that is negative, minus negative 1/3. So we just plus 1/3 because that part is equal to 1. So we just have negative 1 over 3 e to the negative 3b minus a negative 1/3 is plus 1/3. Yeah. So that is 1, and multiplied by 1 it's just that, right? Now, when we try to find the limit, put infinity in there. You know what? I think it's better just write like this. E to infinity this is not right. It is. It's not very good to write the notation like that, but it's easy to remember. I said it is wrong to write like this, but yeah, but it's easy to see, right? So e to the negative infinity is approaching to 0. So what make this not perfectly correct? This should be approaching to infinity and not equal to. So that's all. Right. Usually we have the limit. We're not going to write like that mathematically, but right. So now we have put infinity in here, so we'll have kind of. That's why I'm not going to write equal to here. So if we put infinity, that's what we will have. And e to the negative 1/3, I mean this one here, e to negative infinity is equal to 0. So this one go to 0 because e to negative infinity goes to 0. And so that one go to 0, we're left with 1/3. And if it is equal to a number, we say the improper integral is convergent. Okay. Simple enough, right? Now, we'll take a look at this one. First thing we do, of course, replace the limit. Infinity replace the limit with b, and let b goes to infinity. Right. Now, just integrate. And if you see this is a tangent inverse, then that is correct. Where we have that. So I will have x squared plus constant square. We want to make a square here, and that is the tangent substitution. When we do that, that should be tangent inverse. Section 7.5. But let's just do the trig substitution here. Right. First, let x equal to, when we have a constant square plus x squared, that is tangent. X equal to a tangent of theta, but a is equal to 1, so we just have 1 tangent of theta. Take derivative. Derivative of tangent is secant square. And move the d theta over. Right, so we have that. And then next we convert the 1 square plus tangent square. 1 square plus x square, that is. X is tangent square. 1 plus tangent square is secant square. And now we put back everything into the integral. Still have the limit though. Right. On this one I will not change the limit. I'm just going to keep it like that. I said I'm not going to change the limit of 0 and b. I'm just going to give it at the end, I convert back into x, and then substitute back into x. So keep the limit here. 1 square plus x square, that's secant square. And dx is secant square d theta. So cancel everything. So I said I do not change the limit. So whatever the limit here is limit for x. So when we do that, we put it back on x. We do not change. I don't want to change the limit here. Of course, we certainly can change the limit too, but I just don't want to do that. Here, just make sure x is 0 to x equal to b. Secant and secant square cancel out. We just have d theta. Now, integral of d theta is just theta. So if limit of b goes to 0, and that is integral of d theta is just theta. Very careful, we have x equal to 0 and x equal to b. This is not theta, so we cannot substitute in directly. But it's simple enough though. If x equal to tangent theta, so theta is equal to tangent inverse of x. Right? So theta equal to tangent inverse. We have to substitute back in terms of x before we substitute the limits. Infinity. Tangent inverse. Going from 0 to b. And substitute b, substitute in 0. Right. Now let's graph the tangent inverse and see what happened. It is in radian mode, yes. So y equal to tangent inverse of x. What's that look like? Right. So when x goes to infinity, even though this look like it goes to something, but now remember we talk about the domain and range of the tangent and the tangent inverse. The tangent inverse, I'm going to put here. So notice that the tangent, what the tangent look like. What if just tangent of x? Right, look like that. Now, if you focus only when x go to negative pi over 2 to pi over 2, I will change the windows now from negative pi over 2 to pi over 2. Yep. So you see the tangent here is going to be 1 to 1 and negative pi over 2 to pi over 2. There's two vertical asymptotes. So if we turn this to the tangent inverse, the vertical asymptote becomes the horizontal asymptote, where here is pi over 2 and negative pi over 2, and the tangent inverse is like that. Because of that, when we put infinity here, tangent inverse of infinity is pi over 2. So it goes to pi over 2. So this one goes to pi over 2. And the tangent inverse of 0, that easy. tangent inverse of 0, that should be 0. Yeah. Tangent inverse of 0 is 0. So that one is 0. So the whole thing turned into pi over 2. Right? By the way, we could potentially, let's see, can we do this math number 9? Let's go from 0 to a very big number. Let's see how close it is to the actual answer. It might take some time, but okay. So we have that. Now how close is that compared to pi over 2? It's close enough. Usually for this we make it very big. And we don't want to type a lot of 9, we just say 1. As you see the EE, that times 10 to the power of 10. And the answer here is close to 0. So it doesn't work. So what I'm trying to do, say here is, when it go to infinity, don't use a calculator, because that would be extremely misleading. What the calculator do is they do like what we did in the previous section, using the trapezoid rule, Simpson's rule, something like that, to evaluate the integral. Now if we want to go this like 1 billionths. Yeah. The 1 over x squared, 1 plus x squared, look like this. Now the calculator only can choose some, let's say 1,000 points, for example, to evaluate the integral. If we choose 1,000 points, the first point will have some values, but after that, those will be extremely small values. And they just focus on this small values. That's why this is wrong if we use a calculator and use a very big number here. So don't use a calculator to evaluate any of this. Right. Consider the family of function 1 over x to the p power. For what values of this the function converge? So we have different values of 1 over x to the p. Right. Now, remember when we do the integral, the power rule. So when we have the power rule, if we have something like, talk about the power rule, it works if the power is not equal to -1. Otherwise, if it is equal to -1, we have this special case. The integral of that is ln of x, ln of absolute values of x. So, similarly, then we will consider 3 scenarios. One of them, p is bigger than 1, p less than 1, and p equal to 1. Because when it equal to 1, that integral is completely different than other integral. Right, so 3 cases. Case number 1, if p is greater than 1. Right, now we just integrate. Now the integral will become 1 to infinity x to the p dx. Now integral, it just this 1 over x to the p, sorry. And the first thing we do, of course, is we change the limit. And to integrate that, I will change it to a power and use the power rule. And then the power rule. Increase the power by 1, divide by the same thing. And I will use the limit from 1 to b. That limit for x, of course. Now, what are those? Now we have p greater than 1, right? If p greater than 1, we turn to negative first, so multiply by negative 1. So if p is greater than 1, negative p is less than negative 1. Right? Because multiply by negative number reverse inequality. So we reverse from greater than become less than when we multiply both sides by negative 1. Now we will switch and we add 1 on both sides. So we have negative p, negative 1 plus 1 is 0, forgot the plus 1. So when we do that, we have negative p plus 1 is less than 0. Right, so that is significant. When p greater than 1, we imply that negative p plus 1 less than 0. Right. So if this is less than 0, what do we mean by that? Right. So I'm just going to copy this and I'm going to substitute in b for x. And substitute in 0 for x. I mean 1 in for x. Right, so we do that. So now what happens if we put infinity in here? What is infinity raised to a negative power? Think about that. Because that's less than 0, what is infinity raised to the negative power? Right. What's that? So it's difficult to put in the numbers. Let's say the negative 1 or negative 2 or any negative number, right? So when it's negative, we move it down to the bottom. So we have infinity raised to a negative power. So we bring it down 1 over infinity to the positive power. And this is equal to 0. Because finite divided by infinity. So bottom line is this go to 0. Because we have infinity to a negative power is equal to 1 over infinity to a positive, which goes to 0. So that one goes to 0. So we just have this. 1 raised to any power is still 1. So bottom line is all of this one goes to 0, and we just have negative 1 over negative p plus 1. Now take the negative to the bottom. We have 1 over negative to the bottom. One over p minus 1. Now, p is greater than 1, p minus 1 is positive, so the answer is going to be positive. Which makes sense because the area, the function above the x-axis, the area should be positive. Alright, so that's the first case where p greater than 1. Now, case number 2, if p is equal to 0, if p equal to 1, sorry. So we have 1 to infinity 1 over x to the first power because p is 1 dx. I will change the limit. That and 1 over x, just 1 over x dx. So integral of that is ln of absolute value of x going from 1 to b. Now substitute in b, substitute in 1. Now what do we have for the ln? For ln of infinity is infinity, ln of 0 we don't have that. We have ln of 1 is equal to 0 though. We don't have that. So ln of 1 is equal to 0, and that one goes to infinity because ln of infinity goes to infinity. So after all of this, what do we have? Infinity minus 0, right? And because that limit does not exist, so in this case, we say is divergent because there's no limit. Case number 3, if p is less than 1. If p is less than 1, we have the integral 1 to infinity 1 over x to the p dx. Let's change the limit because it is the first thing we do. Right, and then we move to the top. So integral of that, I'll just use a power rule. Now just take a look at what is negative p plus 1. Right. Now what originally we have p is less than 1. Now similar to what we did earlier, If p is less than 1, negative p is going to be greater than negative 1. So reverse inequality again, where we multiply by negative 1. And then we add 1 on both sides. Negative p plus 1 greater than negative 1 plus 1. Right? Just add 1 on both sides. And that gives us negative p is greater than negative p plus 1 is greater than 0. So that is positive. Right? So when p less than 1, negative p plus 1 is positive. And now we have, now let's substitute in the limits. By limit I mean those two. So x is going to be b to negative p plus 1 over negative p plus 1. Subtract, put in 1, negative p plus 1 over negative p plus 1. Right, so what do we have here? Remember, the negative p plus 1 is positive, right? So what we have here is infinity to a positive number, which is infinity. By the way, negative p plus 1 here is also positive. So infinity raised to a positive number is infinity divided by a positive number. So still positive infinity. And 1 raised to any power is 1. So in this one we will have infinity minus 1 over negative p plus 1. Now this is positive. It doesn't matter though. This one is a finite. By finite I mean it's a constant. Infinity minus a constant or plus a constant doesn't matter. It is equal to infinity. So because it is infinity, it is divergent. Right. Once again, because negative p plus 1 is positive, we have the top be infinity go to positive. So the top is infinity, the bottom is positive. Infinity divided by a positive number is still infinity. And that one, 1 raised to any power is still 1. And then negative p plus 1 is positive. So the whole thing is a finite number. Infinity minus a finite number is going to be still infinity. That's why it's divergent. So all of those 3 scenarios, only one case for what values of p, and the answer is when p is greater than 1, it is convergent, and it is equal to this. By the way, you will see this again in chapter 10. But for now, we go to next part of the problem. So we have that improper integral. I think so when p greater than 1, this is convergent. Equal to 1, divergent. Less than 1, divergent. So it only works if it is p is greater than 1. Right, now we're on to this one. First one, always, of course, we change the limits. And we say this is the lower limit. So let's use a for that. So usually the upper limit we use b, lower limit we use a. Alright, now just need to integrate this, and this is typical substitution. So what I do is let u equal to negative x squared. And we'll take derivative. negative 2x. Multiply the dx over so du is negative 2x dx, which implies du over negative 2x is dx. So we have the substitution for dx, and also now we interchange the limit. We change the limit, not interchange, sorry. We originally we have x, after that we have u. So x go from a to 0, u is negative x squared, so u equal to negative 0 squared is 0, u equal to negative a squared. Right, so that will be that. Now substitute into the integral. Still have the limits of a goes to negative infinity. Okay. Now the limit will change. Originally it is x. Now it will change to negative a squared to 0. And that limits for u. Right, we have negative 4x still there. A to the negative x squared, which is u. And dx is du over negative 2x. X cancel out with x. Negative 4, negative 2, bring outside of the integral. Outside of the integral we have negative 4 over negative 2. Right. Don't forget that. Negative a squared to 0. And everything either cancel or bring out the integral. Just have e to the u du. And integral of that is still the same thing. Negative 4 over negative 2 is 2. So bottom line is we have limit of a goes to negative infinity up to e to the u, and u go to negative a squared to 0. And note that those are the number, those are the limit for u. So I'm just going to substitute in for u. Substitute in the limit. That is just fundamental theorem of calculus. Now e to 0 power is 1, so that's easy. Yeah. So e to 0 power is 1, so that is 1. And then what is this? Essentially we have e to negative a squared. A is negative infinity square. Negative infinity square is positive infinity with an extra negative, so we have e to negative infinity, right? Negative infinity square is just infinity, and then we have the negative here still there. Now what is e to negative infinity? Well, that's 0. So negative infinity square, there are 3 negative signs, so it's end up negative. And that go to 0. So we just have 2 times 1. So the answer is 2. Right. So simple enough, right? Right. Next we should do one problem that have both infinity and negative infinity. However, because of I just realized that the space here is not quite enough, so let's just change this to 1 instead of 4. Not much though. Just change that to 1, please. Right, now, when we have both infinity as the limit, what we need to do is split that, and we can split using any number in between negative infinity to infinity. Pretty much any number is between those two. So any number will do. But I'm going to use 0 because that's more convenient. Right. So I'm going to split in 2. I still have negative infinity, but I will go to 0. Let's split to 0. And then I will go from 0 to infinity. So first we can split it like that. Right? So if it is both infinity, we have to split. So we can only handle one infinity at either the top or negative infinity at the bottom. So we can only do that. Right, now let's say in this case, as this integral be the integral number 1, and this integral is the integral number 2. Just 1 and 2. Right. Now let's just evaluate the first one. First thing, we replace the lower limit with a, right? The reason I want to change to 1 because earlier we did this from 0 to infinity. So we know that second integral, this one, we already did that. It is pi over 2. Right? And also we did earlier, this show earlier that the integral of this is tangent inverse. Right? Yeah. So 1 over x squared, the integral of that is the tangent inverse. So this is example 2. Yeah, so that's why I changed to 1, so we don't have to do much of it. Or this is tangent inverse if we remember that already. Right, so we have this is tangent inverse of x, because we did that earlier. The integral of that is tangent inverse, and this one goes from a to 0. So pretty much what we have is tangent inverse of a minus tangent inverse, 0 first. Tangent inverse of 0 minus tangent inverse of a. Now, remember this is the graph of tangent inverse, right? When x go to negative infinity, it go to pi over negative pi over 2. So what we have is tangent inverse of negative infinity is negative pi over 2. So that one go to negative pi over 2. And tangent of 0 still 0. So this integral equal to 0 minus negative pi over 2 is also pi over 2. And from the previous example, we have this one go to pi over 2. From example 2, the second integral equal to pi over 2. So when we add this together, the integral from negative infinity to infinity is 1 over x squared plus 1 is equal to pi over 2 plus pi over 2 is pi. Right. Just one little thing that I want to mention here. Notice the function of 1 over x squared plus 1 right. So that is the graph. I will change a little bit. Let's go from that's negative 5 to 5. But the y values, let's say it go from negative 1 to 3. So the graph of that is a bell curve. What's significant of that is it is symmetry, right? There's the left half and the right half is the same, because this function is an even function. Even function is symmetric on the line y equal to x. Now, if the area on the left is equal to a finite number, the area on the right is also a finite number, because that is symmetry. Now, if one of this equal to infinity, or we say divergent, then we cannot say that. Infinity on this side, the other side might be something. It could be infinity too, but if one of this is infinity, then the whole thing is divergent. We don't care about what happened on the other side, right? Now, let me say that again. We split that in two integrals. If one of them is infinity, then we just say it is divergent. That by definition. Later on, of course, we might have the potentially, if the function is not the bell curve, it is like this. So one of them is infinity and one of them is negative infinity. And then we say, what happened if infinity minus infinity? Well, that is indeterminate. So, by definition, emphasize that. By the way, this one, somebody define this to be 0 if the graph is like that. However, the way we define it is, if one of this is divergent, the whole thing is divergent. So in this case, ignore that. If one of them is infinity, the whole thing is divergent. Right. Now we've covered the first part of it. The first part of the improper integral is where we have the infinite interval. So the limit is infinity or negative infinity. Now, what we see here is, suppose the function is continuous. Now what change here is, it is that, meaning that the function f of x at a is undefined. So in that case, if there's a problem at a, we have to deal with that. Just make a change. If the problem at b, if the function is undefined at b, change the limit to that. And if there's a problem anywhere in between, we have to split. And then, of course, from a to b, we just split from b to a. And just like what we said before, if both of this exist, then the whole thing exists. If either one of them is divergent. If either one of them is divergent, the whole thing is divergent. Of course, divergent is when the limit does not exist, and otherwise is convergent. So this is pretty standard here. Right. Now let's look at first example. I don't want to make it more complicated than it should be, so let's change this to 0. Right. rectangle a little more manageable. Right. So what happened when we have that? So what's wrong with this? So let's graph the function 1 over 9 1 over square root of 9 minus x squared, right? Graph. Oh, what's wrong with that? Right. So what's wrong with that? Now, notice we go from 0 to 3, right? So when x equal to 3, there is the vertical asymptote here at 3. So that's why it's wrong. So what we focus here is we say f of x equal to 1 over square root of 9 minus x squared is undefined. Is undefined at x equal to 3. Because 3 squared is 9, 9 minus 9 is 0, divided by 0 is undefined. So in that case, we say f of x is defined and continuous only for x equal to 0. For this problem, we only care about from 0 but 3. Not including the 3. Right, now, if we draw the line from 0 and to 3, and we talk about this interval, this is on the left of 3, so yeah, so we should say 3 from the negative sign. Anyway, so that integral only work from the negative sign, from the left side of 3, because this goes from the left side of 3, right? So that's why there's the minus. But when we write like that, it is improper integral. So we have to replace the whole thing here. Upper limit, so let's use b. Integral from 0 to b of square root of 9 minus x, still 1 over, sorry. Now, when we do this, notice 93 square, right? Still have the limit. Three square minus x square. So we will do the trig substitution. When it is a constant square minus x square, that is going to use a sine theta. So let x be 3 sine theta. And then we'll take derivative. Let's hope I have enough space here. Derivative is 3 cosine theta. A is 3, so that's why 3 sine theta and 3 cosine theta. And then dx is 3 cosine theta d theta. right? And 3 squared minus x squared equal 3 sine squared equal 3 squared minus 3 sine squared. That gives us 3 squared minus 3 squared sine squared. Factor out the 3 squared. Of course, that's just 3 squared cosine squared. Right, you should see that from the get-go, but now substitute this in here. Hoping I have enough space here. Right, square root of that. And dx is that. That's the limit. Right, and square root of that, so that cancels out. So the bottom is 1 over 3 cosine theta. And that cancels out nicely. So we just have limit of b goes to -3 and go from 0 to b. And then just d theta. Sorry, I run out of space, so I have to write extra small. However, what important thing here is those limits we did not change when we do the substitution. So this limit is for x, not for theta. Just want to emphasize that. The limit here is for x. Now, so integral d theta is just theta, right? So we're going to have theta. That go from x equal to 0 to x equal to b. Yeah, so we have that. Now what is theta? That's easy to do. X equal 3 sine theta. So sine theta is x over 3. So theta is equal to sine inverse of x over 3. So we have limit when b go to 3 from negative sine inverse of x over 3 or from 0 to b. Right, and when we put in the limit, we have b over 3 sine inverse of b over 3 minus sine inverse of 0 over 3. Right. Now b is 3 and 3 over 3 is 1. So what is sine inverse of 1? Sine inverse of 1, that is pi over 2, and sine inverse of 0 is 0. So this, when we do that, sine inverse of 1 is pi over 2. and sine inverse of 0 is 0. So the answer is just pi over 2. I just move this up and then have more space here, but right. So standard substitution, the integral of this one is the sine inverse of x over 3. I just could just do that, and then the still from 0 to b. So sine inverse of b over 3, but b go to 3 from the negative side, doesn't matter. Sine of 1, sine inverse of 1 is pi over 2. So we have pi over 2. Sine inverse of 0 is 0. Pi over 2 minus 0 is pi over 2. So that's what we have. Right. This one, I'm not sure if we have enough space. So we have this. Well, now what's wrong with this? Let's graph it. One divided by square root. I mean, not the square root. That's the cube root actually. I see the graph. I will zoom to the standard windows though. Right, so that should be the graph. Right. So there's a problem at 2, because when x equal to 2, 2 minus 2 is 0, divided by 0 is undefined. Because of that, there's a problem at 2. So if there's a problem at 2, we have to split. In this case, we split at 2. Right. First of all, if f of x equal to just a function though. So this function is undefined when x equal to 2. So it's undefined, x equal to 2. So if we put 2 in there, it's undefined, so we have to do something else. So we said it is defined. It is defined. We only worry about from 1 to infinity. We don't really worry about negative infinity to infinity. But so in this case, we say define from 1 to 2, but not including the 2, and then from 2, but not including the 2 to 10. Like I said, only focus on 1 to 10. We don't worry about what happened, positive or negative infinity. Right. So in this case, this integral we have to split in 2, one of which go from 1 so including the 2, not including the 2 from the left side, and this from the right side. So in this case, from 1 to 2, but from the left. And then we do the other one from 2, but from the right. Because it's undefined 2, we just have to skip it. Right. Now it's more than just undefined at 2. The reason we split to this because it has the vertical asymptotes. By the way, if it is undefined in the sense of there's a gap like this, potential we do that too. But this is because of there's an asymptote, so we split like that. Right, and we just do both of them. Right. I said I probably won't have enough space to do this. Let's say we already use that. So let's say this is equal to the first integral is a, and the second integral is b. Right, let's do a first. So we do that first. Now there's a problem with the limit. So upper limit, that will be b. Right. Now we'll do the substitution here. U equal to x minus 2. So derivative is 1, and therefore du is dx. Might be able to put that here. And then the limit. Originally x equal to 1 to x equal to b. When x equal to 1, u is equal to 1 minus 2 is minus 1. And when x equal to b, u equal to b minus 2. Right, and then we substitute in the integral. So the integral a equal to limit b to the 2 negative sign. The limit now change to, instead of 1 to b, it is negative 1 to b minus 2. And the integral here is 1 over u to the 1/3. Dx is du. It's not that bad. That is integral of u to the 1/3. Move that to the top, becomes negative 1/3 du from negative 1 to b minus 2. Now integral of that is u to the increased by 1, negative 1/3. Negative 1 over 3 plus 1 is 2 over 3. Limit is negative 1 to b minus 2. Right? Divide by 2/3 is multiply reciprocal. So that would be 3/2 u to the 2/3. From negative 1 to b minus 2. substitute b minus 2 and minus 1 in here. Three halves. B minus 2 to the 2/3 minus 3 half. U is negative 1 to the 2/3. Now, since b go to negative 2, that one go to 0, right? So 0 to the 2/3, that one go to 0. So what is, right, because b go to 2, 2 minus 2 is 0, 0 to any power is still 0, except for 0 to 0 power. But anyway, so that one go to 0. What is negative 1 to the 2/3? It's positive 1. So this equal to negative 3 half times 1, which is negative 3 half, right? Because this is equal to 1. So negative 3 half. Right, great. We actually can fit the problem in here. So that is the integral b. Now the integral a. Now the integral b, we'll do the same thing. Luckily, this has the same integral. By that I mean the same integral. So the substitution is different, but after that we can just say all of the integral equal to 3 half u to the 2/3. The answer is still the same thing. So that's the nice thing about this problem. Right, substitution. It's still the same thing. X minus 2 to the 1/2. I mean, just x minus 2. So in that case we have the same thing. Du over dx is 1. So du is dx. Also changing the limit. X equal to 10. X equal to a, lower limit. U equal to a minus 2. And when x equal to 10, u 10 minus 2 is 8. So the integral b is equal to still have limit when a go to 2 plus but now we change, instead of going from a to 10, it go from a minus 2 to u to 8. A minus 2 to 8. And then we have 1 over u to the 1/3 du equal to dx. Alright, luckily the integral are the same, so we just take this result. So from the previous example we just say this equal to three halves u to the 2/3, and the limit, the only thing that changed are the limit from a minus 2 to 8. Now it's going to be 3 halves of 8 to the 2/3 minus 3/2, and now put a minus 2 there to the 2/3. Now what is a to the 2/3? That is 4. 4 times 3/2, so we have 3/2 times 4. And then when we put 2 in here, that's 0 to the 2/3, so this one go to 0. Because 0 to the 2/3 is 0, so that's 0. And so 3/2 times 4 is 6. And so we have negative 3/2 on one side, 6 on the other side, and put it back into our problem. So that integral equal to negative 3/2 plus 6, which is 4.5 or 9/2. Yeah. So let's see if we can do the calculator here. Alright, we'll go from 1 to 10. Like I said, even though if it works, we will never use a calculator to verify this, because this is improper integral. The behavior is unpredictable. Right. Let it running. Right. Now we'll go to more example. Let R be the region bounded by the graph of y equal to x to negative 1. So just write 1 over x. Wow, that's actually very good. That is close to 4.5, which is 9/2. But like I said, improper integral is unpredictable, so the calculator, do not rely on your calculator for that problem. Especially, as mentioned before, if x goes to infinity or negative infinity, that is, the calculator doesn't really work at all. But yeah, like I said, that is not bad at all. But we cannot rely on this. Let R be the region bounded by the graph of y equal to x to negative 1. So we have that. Let's rotate this about the x-axis. So we only have this part here. Rotate about the x-axis. We'll actually not have just have that part, we have this region too. So we're talking about this. And we rotate about the x-axis. And we're trying to find the volume. So is this or the washer method or a shell method? I'm going to use the disk here. Let's use the disk or the washer method. Now the axis of rotation is horizontal, so this is going to be the x. X will go from 1 to infinity. Right. First of all, horizontal axis of rotation. So that's going to be dx. And also, because the axis of rotation is the edge of the region also. Yeah, so it the bound by that function and the x-axis. So, and it rotate about the x-axis. So if it is the same thing, so this the same axis of rotation as the edge of the region, that's going to be the disk method. So it's just one radius. Then we put everything here into it. R is from the axis rotation to the edge of the graph. So R is equal to the function which is 1 over x. And we substitute in here. I will take out the pi. Have that. Of course, we can do the improper integral like we did before, but actually we did something similar to it. And we have this case. Right. So in general, for that one, if p is bigger than 1, in this case, p is equal to 2. So that's certainly bigger than 1. So from that example, we can say this one equal to pi times 1 over 2 minus 1. So this is equal to pi. It is because earlier we have from the previous example. What is this example? C3. Yeah, so in that example, that's what we have, and so that's what we do. Of course, we can just do the substitution and all that. Right. So anyway, it's equal to pi. Now, what is the volume of the solid generated by that revolving about the y-axis? If we have this part here, rotate about the y-axis. I'm just going to set this up. So V equal to, now if rotate around this, we can use a dishwasher or a shell. Now the y-axis is the vertical axis of rotation. So it depends, we use dishwasher or shell. So if I want to keep the dx, if I'm going to use dx, which is not parallel to the axis rotation. So if we have axis rotation and we slice in it, it will be the same as the y-axis. Now, so this is not slicing. What we do is actually we're going to wrap around it, wrap around the y-axis. So the thickness is increasing along the x-axis, along this axis. So in that case, actually we use the shell method here, because the axis rotation is perpendicular to the increment, the dx. Shell method is 2 pi RH, and still dx that go from 1 to infinity. Right. The radius from axis rotation to that, and then the height is just that. So the height is equal to the function minus 0, and we use x, and the width, and the radius, pick a point here is x and y. The coordinate of that point is x and y, and since we use dx, we're going to take the x coordinates. Right. So I will zoom it out and let's just write we have the function like this. That is the height. And to speak upon that, the coordinates x and y. Since we have the integral that have x in it, we're just going to use x as the radius. The x is that. Which just happened also from the axis rotation to that point. So this is also x. And so we have 2 pi r h. And of course when we have this, of course x and x cancel out. And of course this is point P equal to 0, so this is divergent. Because that's just 2 pi x, and x go from 1 to infinity. Put infinity in there. Of course we should use the proper the notation for the improper integral. Should never do this. But we know that is divergent. Let's not do it like that. Proper notation. Two pi dx let's evaluate the integral here. Two pi x go from 1 to b. What is the point of using that without using it? Never mind, should be that. Now put in infinity. Put in b and put in 1, and after all we just have infinity in here. That of course is infinity. Right, so that's infinity. Right, now I just want to mention this real quick. This is called the Panther Paradox, the Gabriel horn or Teresa trumpet. The Gabriel is an angel, and this is like a trumpet or horn. Pretty much the angel will blow the horn here, and when we hear it, that will be the end of time. So pretty much that's what the story was about. Teresa is the guy that in chemistry that is dealing with pressure and stuff. So, and the Panther Paradox. The reason we call this is the Panther Paradox is because the volume of this one we calculated earlier. The volume of this is finite, but the surface area, we did not do surface area in here. We do surface integral in calculus 3, but it can be shown that the surface area of this object is infinite. Right, now it says here, this is called a paradox because typically, let's say if we are a painter, we have a bucket of paint, and the bucket is full of paint. If you take the paint inside, it will be more than enough to paint the surface on the outside, right? So that is conventional wisdom. If we take the paint inside of the container, this will be more than enough to paint the surface area. However, not in this case. The volume is the pen inside is finite. That certainly is not enough to paint the surface on the outside of the horn. So that's why it's the paradox. Right. So like I said, this is a classic example. So I thought I could mention it here. But other than that, that's everything I want to cover in this section. So see you in another video in Calculus 2. As always, thank you for watching.